Good morning, everybody. So just a quick comment about the homework. Please, if you're having problem with the homework, email me. We can do a Zoom meeting. We can go over the problems. The homework is not meant for you to understand the concepts of filters and all that. It's meant for you just to brush up on MATLAB. So later on, if we, doing MATLAB, I don't want to look and it's like, oh, I have no idea what this MATLAB is. At least you're familiar with it, and we're going to be assigning more of the MATLAB.
One question: Do you want us to also upload like the program we use like in the MATLAB?
I mean, what I'm going to tell you, and this applies to probably every assignment. Imagine yourself 5-6 years from now wanting to do something similar. Does that make sense?
Yeah.
And then you feel like, oh, we've done something similar. Whether you're at work or whether you're working on a project where you have to do some MATLAB. You go to the assignment, oh, great, I have the assignment. You look at the assignment, oh, it's missing the MATLAB code. See the problem? So always attach everything for yourself if you were to look at it later. Make sense?
Like, do you want us to upload it for the homework?
Yes, well, that's what I'm saying. I mean, with the homework, just add it as an appendix. So you always have it in one place.
Okay, so like screenshot it, copy and paste it into the document.
Copy and paste it to the document. So you have access to it. Again, the point is, I'm not going to look at it. Just do it for yourself so you always have access to it. Okay. Any other questions, comments? Okay, so in the previous class, we introduced the discrete time Fourier transform. Is this concept make sense? Okay. We started with the Fourier transform. We calculated the Fourier transform. Then we said, okay, we have a discrete time signal. We're going to generate an impulse train. Then we calculate the Fourier transform for it. And then we got the expression for the discrete time Fourier transform. And this is the expression. We have the expression for the inverse discrete time Fourier transform. And then we've done an example, lots of calculations, but hopefully the example, is straightforward. So what we've done is we came to this signal that was a rectangular pulse and we sampled it. We took samples from it. This became discrete time signal. We took the discrete time Fourier transform. And this is what the discrete time Fourier transform, the formula for the discrete time Fourier transform. And we stopped at this one, isn't it? Now what we're going to do, we're going to plot this discrete time Fourier transform and see how it looks like. And then we're going to try to compare it to the Fourier transform. So if I come here and look at the expression, that we got from here. So this was our x of omega. Or x of e to j omega, either way. What is this going to look like? If I were to plot this, it's going to look like a sink. Agree? What is the value when omega is equal to 0? Going to equal to? What is, okay, so the x-axis is the omega. What is the value of this sink when omega is equal to 0?
Max.
L'Hopital's rule. Omega over 2 going to cancel. 2n plus 1. Make sense? It's going to, if omega is 0, this is going to be 0 over 0, which is going to be infinity. We can take the derivative of both. So therefore, it's going to equal to 2n1 plus 1. Everybody agrees? Anybody confused? Okay. So therefore, x at 0 is going to equal 2n1 plus 1. Also, I can calculate when is this crossing happening. At what frequencies this curve is crossing the real axis. So x of omega is going to equal to a 0 when omega over 2 multiplied by 2n1 plus 1 is equal to plus or minus n multiplied by a pi. If I have a pi here, the sign of a pi is a 0. So anytime this argument is a multiple of pi is going to result in a 0. So therefore, omega is going to equal to 2 plus or minus 2 multiplied by n multiplied by pi divided by 2n1 plus 1. Agree? Again, this 2 is just multiplying across. 2n pi divided by 2n1 plus 1. Okay. Now if I compare, now one more thing that is important to keep in mind. If I were to continue to plot this curve, how is it going to look like?
It's going to approach 0.
It's going to decay. What else?
It goes on infinitely.
No. It's going to be periodic. You remember? We said x of omega from the previous class is equal to x of omega plus 2 pi. Where did we say it? X of e to j omega has a period of 2 pi. Why? Because this argument here, if I add to it a 2 pi, is going to stay the same. Does that make sense? So what that means is that when I come here and I plot this, this is 0, this is omega. At 2 pi, I'm going to get the same curve that looks something like this. At negative 2 pi, and so on and so forth. Does that make sense? Everybody? So x of omega is periodic with period that is equal to a 2 pi. If I were to plot from negative pi to a pi, I would have covered all the frequencies. Now that makes sense, it's consistent with what we already know. Why? Because for discrete time signal, what was the frequency range that we said we can have the signal have? From 0 to 2 pi, or from negative pi to a pi. Make sense? What we already know from before is that from this frequency, negative pi to a pi, we are covered all the frequencies. Any other frequency in discrete time falls in this range. Any other frequency is just the same as one of these frequencies. So it makes sense that if this frequency is the same as this, then this has to equal the same thing. Is that clear, everybody?
Okay.
Okay. Now what we're going to do is this. I'm going to compare this graph that I have with the graph that we have generated of the Fourier transform. So if I look at this graph here, and if I look at the graph that we generated from the Fourier transform, what do we notice? They look the same. They have the same shape. If I look at this curve, and I take the curve from negative pi to a pi, up here, this looks like the Fourier transform. The only difference, this is equal to 2n1 plus 1. The other one was equal to 2t0. Does that make sense? So therefore, we can say that in the range of omega between negative pi and pi, x of e to j omega looks similar to x of w, the Fourier transform. The only difference is that it is scaled by 1 over t. Let's call this t or t sampling. Where is this coming from? If I look at the magnitude of this at omega equal to a 0, what is it equal to? What is it equal to? When omega is equal to 0, the magnitude is 2n plus 1. What was the magnitude of the Fourier transform? Anybody has it? When we calculated, it was equal to 2t0. So if I divide the magnitudes, what do I get? I'm going to get 2 to 0, or 2n1 plus 1, divided by 2 to 0. Agree? The ratio of the magnitude when omega is equal to a 0. But what is this approximately equal to? This is equal to 1 over Ts. Make sense? Does not, because we did not define what Ts is. What is Ts? The sampling time. What I'm saying is, so to put this together, if I came to this rectangular pulse and I sampled it, what is the sampling time of this pulse? If I took 2n samples, then it's going to be 2t0 divided by 2n. Does that make sense?
Yeah.
So this that I have here, if I take 2 to 0, which was the width of the pulse, divided by the number of the pulses, is going to give me approximately the sampling time that I'm using. Make sense? Everybody?
Yeah.
Okay.
Real quick, sorry, for it says in the range of omega between negative pi and, that's supposed to be negative pi
And pi.
Okay. Thank you.
You're welcome. Okay, so therefore, so what I'm going to do, we're going to finish this, then we're going to add another transform just to make things simpler and more confusing, and then we'll run MATLAB and we'll show it all together in MATLAB. Sounds good? And I'll post the MATLAB code, so please, when you go home, run it, become familiar with it, and if you have it, if you understood it, then you're in great shape. Okay, so to summarize, the relationship between discrete time Fourier transform and Fourier transform, if I have a continuous time signal, if I sample this signal to get a discrete time signal x of n, then if I take the Fourier transform, I'm going to get x continuous of j omega. If I take the transform, the discrete time Fourier transform, I'm going to get x of e to j omega. And I'm sampling at Ts, T sampling, where Ts is equal to 2 pi divided by omega s. Together? This is clear? We're sampling every ts second. Omega s is equal to pi over ts. If I have a signal, I sampled it, I'm going to get x of n. If I take the continuous Fourier transform of the continuous signal, I'm going to get x continuous. If I take the discrete time for Fourier transform of the discrete signal, I'm going to get x of e to j omega. So we can say in the frequency range in the frequency range where omega is greater than negative pi and less than or equal to a pi, which corresponds to omega greater than negative omega s over 2 to omega s over 2. What is this frequency when omega is between negative pi and a pi? If omega is equal to a pi, what is that frequency corresponds to? Anybody? Omega is equal to W multiplied by T, S, isn't it? How does omega relate to the continuous time frequency? Omega, the discrete time frequency, is equal to omega multiplied by T. Agree? Everybody? This is from second, third lecture. Anybody confused? Yes, no? Clear? Okay. So if omega is equal to this, when omega is equal omega s over 2, so if omega is equal omega s over 2, then if I substitute it here, I'm going to get omega s over 2 multiplied by ts. But what is omega s equal to? 2 pi over ts multiplied by 2 multiplied by ts. Ts cancels 2 cancels, corresponds to a pi. Make sense? Is it clear or confusing?
So, are you saying omega is equal to pi here?
Omega, when omega is equal to a pi, that corresponds to W equal to omega s over 2. And when omega is equal to negative pi, that corresponds to a frequency that is negative omega s over 2, which is all coming from the relationship between omega and W. Omega is equal to W multiplied by T. When omega is equal to omega s over 2, what is omega s? 2 pi over Ts multiplied by T. T with T is going to cancel. That's going to correspond to a pi. Make sense? I mean, we're going to be seeing this throughout, so I know the first time you see this confusing, but again, the range of omega between negative pi to a pi corresponds to W between negative omega s to omega s over 2 over 2. Good? Okay. Okay, so in this range, x of e to j omega approximately equal to 1 over t x continuous of jw, and where omega is equal to w over t, or ts if you like. Make sense? And that's what we showed in the graph that we did for the using discrete time Fourier transform and the Fourier transform. In this range between pi and negative pi looks similar to the Fourier transform between negative omega s and omega s. The only difference, it was scaled by 1 over t. Together?
And that T at the front can also be set as TS.
Well, whenever we refer to T, we are referring to TS. T is TS. Okay. Together, everybody? Ask if there's any confusion. Okay. So therefore, we can say that the discrete time Fourier transform of a sampled signal is approximately a magnitude scaled and frequency normalized version of the Fourier transform. For the same signal, of course.
You keep like saying that over and over again. I guess it's important, but
But not sinking in or not accepted?
well, you keep saying it in different ways.
Yeah. So, go ahead.
No,
Object if you like.
no,
All what we're saying is that here is the Fourier transform of this. It looked like this. Of the continuous time signal. I took the discrete time signal. It looked exactly like this. So what we're saying, okay, if you took a Fourier transform, you got this. If you look at the discrete time Fourier transform, it also looks like this. What we're saying, okay, this looks like this. That's like all this saying is we're saying this curve is the same as this curve. Where is as this curve that we just did here? All what we're saying, that curve is the same as this curve. Make sense? The only difference, this was 2m plus 1, that one was 2t0. But then we said, okay, if I take the ratio of them, that's approximately equal the sampling time. Make sense?
Yeah.
Now this is going to repeat from negative pi is going to repeat. So we said, okay, then I cannot compare them from negative infinity to infinity. I can only compare them from this range to this range. This range to this range is similar to the Fourier transform. But then we said, okay, this omega is equal to negative pi and a pi. What is this? If omega is equal to a pi, what does that correspond to in the continuous frequency? We said omega is equal to W multiplied by T. If omega, this omega is equal to pi, that corresponds to omega s over 2. Make sense? Trust me, this will be like the alphabet in few lectures. You will accept it, becomes without, you're going to be like, oh, why did I not think of this even before this class? Okay. Ready for the next? Okay. We're going to build on top, so tell me. Okay, so now the question that we're going to ask is, can we calculate the Fourier transform or the discrete time Fourier transform on a computer? Yes or no?
I don't think we can do the discrete.
Okay, majority said no. We'll go with the vote of the majority. The Fourier transform says, oh, if you want to calculate me, you have to integrate from negative infinity to infinity the continuous time. This is the definition of the Fourier transform, negative j omega t dt. Can we do this on the computer? When we say on a computer, on a processing unit, you have a microcontroller that does calculation. Can you do it? No, you don't tell me, oh, MATLAB has symbolic toolbox, it can do this calculation. That's not what we're referring to. Okay. What about the discrete time Fourier transform, where you have to calculate x of e to j omega equal to the summation from negative infinity to infinity x of n e to negative j omega multiplied by n? Can we calculate it with a computer? Okay, nobody want to answer? I'll answer for you. The answer is no. Why is it no? Well, yes, excellent. We have infinities. So the problems with both of these expressions is in both cases the frequency variable is continuous. Agree? So if I want to calculate x of omega is a continuous variable. Computer is not going to be able to calculate a continuous variable. Make sense? The second problem, in both cases, we have an infinite summation or integration. And in the case of the Fourier transform, we have to do integration. Together? So apparently, we cannot use these expressions. I gave you a microprocessor and told you go calculate these. You're going to tell me I cannot calculate them as they are in this form. What would you do? If I want to use it using a computer, I'm going to approximate it. Make sense? So the solution to these problems we're going to approximate Fourier transform on a computer. So what we're going to do, the first thing, we're going to replace the continuous time signal by a discrete time signal. Make sense? You give me a continuous time signal, I'll tell you I cannot handle it. Give me samples of that discrete time signal. So that means I'm going to replace the Fourier transform with the discrete time Fourier transform. Since now the signal is discrete, I'm not going to be able to calculate Fourier transform, but I can calculate the discrete time Fourier transform. Can we do it as is? No, not yet, because we need to truncate x of n to a finite number of samples. Make sense? What the discrete time Fourier transform says, the expression for the discrete time Fourier transform, I have a summation from negative infinity to infinity. I cannot do this on a computer, therefore I have to truncate it. So therefore, I'm going to replace the summation from negative infinity to infinity with the summation from n equals 0 to n minus 1. Together? Now, of course, in the example that we've done does not apply because the example that we just did, it was a finite number of samples. It just so happened, in general, the signal is not going to be a finite number of samples. Does that make sense, everybody, what I'm saying? So this case does not apply to the previous example. The previous example already a finite number of samples. But in general, a signal can go from negative infinity to infinity. It's infinite. So we're going to truncate it to n. And then what we're going to do is we're going to sample in the frequency domain. Therefore, we're going to replace omega by 2 pi k divided by n in the range where k is between 0 and n minus 1. So remember, omega and w are continuous variables. So in order to handle them, we're going to sample them. We're going to take samples of omega. And therefore, we're going to be replacing omega by 2 pi multiplied by k divided by n. Together? Okay. All these, now we're going to come back and study this in more details, but again, we're going to be needing this before we introduce it formally, and therefore that's why we're doing this a quick introduction of it. All this leads to the definition of discrete Fourier transform. And what the discrete Fourier transform says, x of k is equal to the summation from n equals 0 to n minus 1, x of n e to negative j 2 pi n multiplied by k divided by n. And k is between 0 and n minus 1. And the inverse discrete Fourier transform is x of n is equal to 1 over n summation from k0 to n minus 1. This is capital letter x, that's a small letter. This is capital letter of k e to j 2 pi nk divided by n. And this is for n between 0 and n minus 1. What is it we've done? Well, what we've done, we said you want to calculate Fourier transform, we cannot calculate it. We said sample the signal in the time domain. If you sample the signal in the time domain, you're going to be able to calculate discrete time Fourier transform. But the discrete Fourier transform is a continuous variable. So we said instead of calculating the discrete time Fourier transform at the continuous variable, sample omega. So now we're going to be calculating the discrete time Fourier transform only at these frequencies, at only these values of k. Does that make sense? Any questions? Okay. So, to summarize all this, all what we're saying is that you can calculate on the computer x of k. This x of k is the discrete Fourier transform. This is approximately equal to x of e to j omega when omega is equal to 2 pi multiplied by k divided by n. And this approximately equal to 1 over t, the continuous j omega when omega is equal to 2 pi k divided by n multiplied by t. Anybody with me?
that box, the definition?
This is x of k.
Okay.
X of k, this is the discrete time Fourier transform, this is the Fourier transform. Make sense? With me? So this is the discrete Fourier transform, this is the discrete time Fourier transform, this is the Fourier transform. And all what we're saying is coming at this example here. I want to calculate this curve on the computer. This curve is continuous. I cannot do it. What do? I'm going to sample it. I'm going to come here to this curve and say I cannot calculate all the values, but rather I can take samples here and calculate them. At this value, this value, this value, this value, this value, this value, this. Make sense? I'm going to come here and say, okay, what is this frequency? Calculate it with the computer. What is this frequency? Calculate it, calculate it, calculate it, calculate it. This, the one I plotted in gray, is the discrete Fourier transform. The one in blue is the discrete time Fourier transform. Does that make sense? Everybody? Anybody have question? Question? Okay, forget the details of this. Forget the details. Is the concept clear? We have a continuous time. If I want to plot the, I want to calculate the Fourier transform of a continuous time signal. Can I do it? I cannot. Continuous time signal. What do we do if I want to go to the computer?
You got to sample it.
I'm going to sample it. If you sample it immediately, what are we talking about now? Discrete time Fourier transform. Now the discrete time Fourier transform requires a summation from negative infinity to infinity and generate omega that is continuous. I cannot do it on the computer. What do I have to do? I'm going to generate at certain points. Make sense? That certain points, calculating at certain points, is the discrete Fourier transform that we just introduced.
Okay.
So visually, you should be able to see all these. Make sense? Okay. Now, before we continue, let's run a MATLAB and show you what we are talking about. And tell me MATLAB does not exist. Which it does not.
You gotta open up your Citrix.
Citrix does not exist.
I know for a fact both of those were on this computer last night.
Which one?
Well, the apps that you just searched up on the toolbar, I know they both exist last semester on this computer.
Yeah, well,
Oh, I think it gets wiped every semester.
yeah. And I don't think it's in Argo App Lights. Does not exist. Okay.
Go to
It's there.
access.
It was?
It's there. That's how I've been using it.
Press Control Shift T, close to it.
I closed it.
You gotta go to the apps.
Yeah. You need-
Oh, and the apps. Okay, okay. Yes. Yeah, good. Okay. Here's my. Okay, so we're going to go with the backup plan. The backup plan. Oh, I have. Oh, there we go. As this is going to be just as good as showing this. So this is a screenshot of what you're going to get when you run the code. Yeah, I mean, this is going to be, I mean, this is on the G drive, so it's not going to be even,
So you gotta log into your.
yeah, it's just more involved. Luckily, we have the backup plan. But nevertheless, I have the code also in the node, so when you can probably copy paste it. So this is the code for each one of these graphs. And these are the graphs of what we want. We have this, a pulse that we've just done. We calculated the Fourier transform for it. This is the plot of the Fourier transform. Make sense? Then I came to that pulse. I sampled it. Now I have these samples of this pulse. Now this index is the, what is this axis? Samples, N. What is this axis? W. No, this is the spectrum.
That's frequency.
The frequency, W. Omega, or frequency, or W in frequency in hertz, or W in radian per second. Now what I did, I calculated x of omega. This is x of omega of this discrete time signal. What does it look like?
Looks like the original.
It looks like the original one, isn't it? So let me zoom and make it smaller. What's the difference between them? The magnitude. And this is where it is going from to negative pi to a pi. You see it? From 3.14 to 3.14. If I were to extend this, how is this going to look like? It's going to start repeat. However, in this range here, this corresponds to the range here.
Yeah.
From negative omega s over 2 to omega s over 2. This looks like this. Make sense?
Mm-hmm.
Now this I cannot calculate using the computer. This I cannot calculate using the computer. Why can't I not calculate this using the computer?
Because it goes on forever.
Because I have integration, isn't it? And it goes on forever. Why can't I calculate this using the computer? I can in this special case because it's finite.
Yeah.
But in general, this will go from negative infinity to infinity. I will not be able to calculate this. You get it? So what do? We're going to use the discrete Fourier transform. What does the discrete Fourier transform going to do for me? It's going to generate a graph like this. What is the difference between this and this?
Bottom one is the sample.
These are samples of this graph. Make sense? This is all what we've been doing for the last 3 lectures. What do we call this? Discrete Fourier transform. The computer can calculate it. Make sense?
Yeah.
Now I plotted this with a stem, so to emphasize that these are samples. But if I plotted this continuously, what is it going to look like? It's going to look like this. Make sense, everybody?
Would a computer then be able to translate that Dft graph into something that resembles the original FT?
The computer on its own will not, but I will. Now if I'm studying this signal at the continuous time, what am I going to do? I'm going to change the label of this to the corresponding frequency. I'm going to plot it discontinuously, and I'm going to tell you this is the spectrum of that signal. Make sense? Mm-hmm. Now when I tell you that, that does not mean MATLAB generated that spectrum. It means I understood how this relates to that graph, and I scaled it accordingly.
Yeah.
Is that clear? Makes sense? What MATLAB is going to give you, an array. It gives you an array. But I have to know that this first point corresponds to negative omega s over 2. This last point corresponds to omega s over 2. I have to do it manually.
Yeah.
Make sense? Everybody? What is the MATLAB command that does this?
I think it's this DFT.
FFT. The FFT. What does the FFT do? It calculates the discrete Fourier transform for you. It gives you an array. It does not know where it starts with it. I know where it starts with. This corresponds to negative omega s over 2. This is omega s over 2. Now, if I'm doing this for this signal, I'm canceling this signal, I'm going to label this as omega, and I'm going to have this as negative pi, this is as a pi. If I'm doing this for the Fourier transform, I'm going to label this as w. This is going to be negative omega s over 2 to omega s over 2. Make sense? And then I will scale it with the magnitude to correspond to the magnitude of the Fourier transform. But I'm going to realize in all this, I'm approximating the Fourier transform. And later on, we'll know when is it this approximation is valid, when is it good, and what affects this approximation, making it good or not really good approximation. Any questions? Questions? Go ahead.
Can you just scroll to the top of the page? I want to see if you visualize them.
This is frequency in hertz, so you multiply it by 2 pi to get it in W. Again, you have the code. So the code is on the next page. So you can run it, and each one will give you one of these graphs. Together? However, if you run this and understand it, then you can take any signal and plot the spectrum for it. Because the same thing applies. And this is the same as the one we are doing in the assignment when we're plotting the spectrum of that sync. Isn't it? We're using FFT. That's exactly the same thing. What are we plotting? We're plotting the discrete Fourier transform that corresponds to that. Okay. Okay. Now that we have introduced the tool that we're going to need, we can go back. So in a way, we did an excursion in the course, isn't it? We introduced all these transforms, but we said all these transforms, we're going to need them. So therefore, we're going to introduce them. So when we use them, at least we feel like, okay, we know what we're talking about. So we're going to go back to our main topics. And the topic that we're going to be talking about is the sampling, reconstruction, and the sampling theorem. And our objective is to obtain a mathematical representation of the sampling process. And this mathematical representation will help us determine how a signal can be reconstructed from its samples. Okay, so is it clear what we're doing next? We're We're going to look at the sampling theorem, we're going to look at the construction, and hopefully by the time we finish this topic, we'll have a very clear idea of how we sample the signal, what impacts the sampling, what the aliasing is, and what the spectrum of the sample signal looks like, and how we can reconstruct the signal and get back the original signal, etc. Okay, so why do we need to study this sampling? Anybody?
So we don't lose data that we need.
Excellent. Because if most of the signals we said that we're going to encounter or that are generated might be continuous time signals. However, what is it I want to do with this continuous time signal? I want to be able to process them. How I'm going to process them? With a computer. But if they're continuous time signals, how I'm going to process them with a computer? I'm going to have to convert them from analog to digital signals. Make sense? What does this conversion from analog to digital signal does? It converts the signal to a discrete time signal. I'm going to take the temperature that is measured outside, I'm going to convert it, I have a signal, I'm going to convert it, I'm going to get samples of that signal. Make sense? Then I'm going to do my discrete time system here. I'm going to be filtering this signal that I have samples of. And after I am happy with the output of this filter, I'm going to get an output y of n. What do I have to do with this y of n? I'm gonna convert it back to an analog signal. So I'm gonna have a digital to analog, and I'm gonna generate a continuous time signal y of c. Does that make sense? And this is what we are doing throughout the semester. We're going to start with analog signal, continuous time signal. We convert it to a discrete time signal. Now on my computer, I can filter it, remove certain bands, add a triple band, amplify, attenuate, do whatever filtering I want, till I generate the signal that meets my requirements. Then I can convert it back to a continuous time signal. I have a noisy signal, I can remove the noise and then give you back the signal without the noise. Okay, so this process involves sampling. This process involves reconstruction. And of course, if we are sampling, somebody might say, oh, we don't need to study the sampling, just take as many samples as you need. What is the problem with that?
Figuring out a reasonable limit.
Figuring space, yes, and processing power. If a signal I can sample it every second, why would I sample it every 1 microsecond? If 1 microsecond does not buy me anything. Make sense? If I have a file, and you've probably seen this, if you have a file stored on your computer and you have a certain resolution on your monitor, whether the file is 10 mega or 1 mega, you're not going to be able to tell the difference because the resolution you scale is going to limit what you can see. Okay, so what we're going to be doing is taking this continuous time signal and generating this discrete time signal. So taking this signal, the continuous time signal, and we're going to be generating x of n, the continuous time at n multiplied by t. So this was my signal. I'm going to be taking samples. Okay. So the question that we're going to be answering is how does the sampling look like in the frequency domain? And we're going to see why we do it in the frequency domain, because that will give us insight into the sampling. And second, what are the limits on the sampling time t so that no information is lost? And then we're going to look how to perform reconstruction. Sounds good? Everybody? Okay. So let's look at the model of sampling of the continuous time signal. So if we have an ideal sampler, how do we represent the ideal sampler? We have a continuous time signal, we have a switch, and this switch will close every t seconds. To get a sample of the signal. Now this switch, it closes, takes a value, closes, takes a value. How long does it stay closed?
Very small.
Very small amount of time, yes. Okay, so this t, we're going to call it the sampling period. And if I take 1 over t, that is going to be the sampling frequency. What is the unit of this sampling frequency? The units of frequency in hertz. And omega s is equal to 2 pi multiplied by fs, which is equal to 2 pi divided by t. And this is the sampling frequency in radian per second. And the question that we're going to try to answer is how fast or slow we have to sample in order to guarantee that x of n contains all the information that we need about the continuous time signal x of t. Good? Okay. What should t equal to? Does anybody know?
2 times the maximum frequency.
How do you know that?
It's like Shannon's theorem or whatever, right?
Nyquist criteria.
Yes, excellent. Okay. So that is the conclusion that we're going to come to. But since you know it, we can do it at a faster speed. So what we're going to look at next, we're going to look at the mathematical representation of the sampling process. And hopefully this mathematical representation will help us determine the limit on the sampling time. So what we're going to do, we're going to take the continuous time signal. What we're going to we're going to multiply it by an impulse train. And then we're going to converge into discrete time sequence. And this is our x of n. So we're going to have the continuous time signal. We're going to multiply this by an impulse train, which looks something like this. The summation from k negative infinity to infinity, delta of t minus k multiplied by t. And we're going to also use this symbol to represent it. Delta t. Continuous time signal multiplied by this impulse train. Then it's going to give me a sample signal xs of t here. And then we can convert it into a discrete time sequence. And this represents our ideal sampler. Okay. So what does this impulse train looks like? Pulse train looks like? Looks something like this. So we have impulse, impulse, impulse. This is a pulse train. And this is P of t. And this is the axis. This is at 0. And what is the time between the impulses? Etc. Is that clear? Makes sense? I have an impulse train that goes from negative infinity to infinity. There's an impulse every t seconds. I'm going to multiply this by the continuous time signal. That's going to give me xs of t. Okay. What does this look like when I multiply these? If I have a signal I have a continuous time signal, x continuous of t. Then I have, once I multiply with the impulse train, I'm going to get impulses a signal that looks something like this. And this is t. This is xs of t after we multiplied it with the impulse train. And then I'm going to get the discrete time sequence x of n, which is going to look something like this. Etc. What is the difference between this signal and this signal?
Can you quantize it?
What else?
Magnitude?
What else? Then what is the nature of this signal versus this signal? This is a continuous time signal. Does that make sense? This axis is t, continuous time signal. If I took these values, then I have a sequence. That sequence is x of n. Does that make sense?
Yeah.
So this, I can see it in the lab. I can generate it in the lab. This, I cannot. This is on a computer, stored in a file.
Digital?
Digital. But the nature of it, this is not something I can see in an oscilloscope or a spectrum or a function generator, etc. This, I can see it. This is time. I can take an impulse train. This, of course, ideal, but I can generate an impulses that are very, very narrow, multiply the sequence. I can see this. This, I cannot. This is taking these values and storing them. Does that make sense, everybody? Even though they look the same, they're totally different nature. After I do this, I'm going to take these as x of n, and then I store them. This could be, a song that is stored on your computer. Together? And that's why here, what is the axis? Just the sequence number. This is the first sample, or first sample, second sample, third sample, fifth sample, etc. Okay. So I have xs of t that is equal the summation from n equal negative infinity to infinity x continuous of nt delta of t minus nt. This is x of n equal x continuous at nt. Agreed? Now, of course, notice like we use these square brackets for the discrete time signal and the curved brackets for the continuous time signal. Okay. So what we're going to do now that we multiplied, we're going to look at this signal, this sample signal, and see how it looks like in the frequency domain. Now, in order to do that, so in the frequency domain, we're going to use some information that I'm going to put on the side here. Now we know from Fourier transform and Fourier transform tables, we know the following. If I have a sequence of impulses that looks like this, and I call this P of t, and this is zero t, 2t, etc. This will have the Fourier transform of this signal is going to be also an impulse train. So this is W. This is going to go from negative infinity to infinity. This is P of W. And this is 0. This is 2 pi over T. This is 4 pi over T. And so on and so forth. Negative 2 pi over T, etc. Okay, so from Fourier transform, if I have a pulse train of these impulses, in the spectrum of them is going to look something like this. Another pulse train. The wider these are, the closer these are going to be to each other. This is 2 pi over T. You see it? That's the difference between them. And the magnitude of these is going to equal to a 2 pi divided by T. This magnitude is equal to a 1. Now we're going to put this in a box and just use it. Okay. So what does this signal look like in the frequency domain? I want to see what xs of t, this signal, looks like in the frequency domain. So this signal, xs of t, is equal to x continuous of t multiplied by the pulse train p of t. Agree? What is it going to be in the frequency domain? What is the multiplication going to be in the frequency domain? Convolution. So it's going to have a spectrum that is xs of w, and this x of w is going to equal to 1 over 2 pi, the convolution of x of w convolved with p of w. This multiplication in the time domain is a convolution in the frequency domain. Okay. So therefore, I can calculate what this xs of w equal to. Is going to be 1 over 2 pi, the spectrum of the original signal, x continuous of w, and convolved with 2 pi over t, the summation delta of omega minus k multiplied by omega s. And this is from k equal negative infinity to infinity. What is 2 pi over t? We can call it omega s, isn't it? This is omega s, 2 omega s, 3 omega s, negative omega s. Together? So P of w is this P of w, the summation of w minus k multiplied by omega s. The magnitude is 2 pi over t, 2 pi over t. Okay, what is this going to equal to? This is going to equal to the summation 1 over 2 pi. 1 over 2 pi is going to cancel. We're going to get 1 over t, the summation of x continuous of w convolved with delta of w minus k multiplied by omega s from k equal negative infinity to infinity. Agreed? Because I'm trying to simplify it, but this is multiple deltas. If I'm convolving this with multiple deltas, it's going to equal this, convolve with this, this convolve with this, convolve with this. Okay. Now, because we are convolving with a delta, what is this convolution going to result in? 1 over t, the summation from k equal negative infinity to infinity. And each one of these convolution, this is capital letter, is going to cause x continuous of w to relocate to omega s. Together? What is the convolution of x of w with a delta of w minus kws? X of w minus kws. Make sense? Remember, impulse. If I apply the impulse, I get h of t. If I apply impulse delta of t minus x, I'm going to get h of t minus x. The impulse shift is going to cause x. Convolution with the impulse shifted is going to shift the signal. Okay. So therefore, what this tells me is the following. The Fourier transform of the sample signal is equal to the Fourier transform of the original signal repeated every omega s and scaled by 1 over t. Magnitude scaled by 1 over t. Together? Okay, we'll stop here. We'll continue this in the next class. Any questions?